Hello guys, my name is Azman. You can call me Akmal. My registration number is 24113845. Today I want to present about the Reynold transport theorem. Enjoy the video. In this video, we're gonna talk about the Reynold transport theorem. And the Reynold transport theorem is a method that allows us to use both system and control volume concept to describe fluid motion. So let's start here with picture number 1, and we call the red our system and our blue our control volume, and the control volume is a fixed place, whereas the system is considered a certain amount of fluid. So here at the same time, both of the system and the control volume take up the space. However, at times plus a small bit of time, what you notice is the control volume stays the same. However, our system which is that amount of fluid that we're looking at move. And so what we do is we use the Reynold transport theorem to link the two of them. So we start with the fact over here that the change of some intensive property. So B is an intensive property of the system with respect to time equal rho time. So intensive property that associate with the intensive property times the change in volume, and we do the same thing right here. However, it's our change with respect to time in our control volume. And what we're left with is this equation that says that the time rate of change of some intensive property here of the system is equal to the rate of change of the property as it flow through the control volume. So if you notice that we with respect of time plus the flow is in and out of our control surface, and our control surface are anything that is a surface of our control volume. So let's take a look at a typical problem, and we have this system here. You know this control volume, and we have a velocity which is 2 meters per second, and it has a diameter of 0.07 meters, and have a second velocity here with a diameter of 0.03 meters. We have 1/3 diameters, but what we want to do is find out what the velocity there is. So if we look at our governing equation, the first thing that we see is that this particular problem, since it's a conservation of mass problem, our big B is going to equal mass, which makes the intensive property that's associated with Mat 1. So if you look at the change in the mass of the system with respect to time, that has to equal 0. That when you look the first term of the right hand side, what you find is that this mass does not change in the control volume with respect to time, so that equals 0. So what we left with is that 0 equals, and let's go back to here, the integral over all of our control system of rho. Remember, little b is 1v, which is a velocity dot n, so that the dot product of the velocity and the unit normal coming from the control surface time are direct differently area. So how many control surface do we have here? We have 1, 2 and 3, so we're going to have to set up 3 separate integers looking at all 3 of these control surface. Okay, at least 0 equal the integer over control surface 1, row v and dot n dA surface 2, row v and dot n surface 3, row v dot n dA. Now there are number of things that can make this equation simpler. So first of all, we're going to assume that rho is constant, that is incompressible, so we can take out of the integer, and if we don't that, you notice that we can then cross out rho. The second thing that we know is that our velocity are constant or uniform, therefore they are not a function of area, and we cannot take the entire term out of the integer. So what we left with is 0 equal v1 dot n times 1 plus v2 and lastly v3 and dot n a3. So what of this v dot n again is the dot product or our velocity times the unit normal coming out of the contour surface. So if we have flow in the, then v dot n is negative. If we have flow out, v dot n is positive. So let's go back to our picture again, and if you notice that flow in our v3, so v3 dot n is positive, and our flow out is both v1 and v2. Okay, we're going to the 0 equal v1 is going up plus v1 a1, v2 is leaving, so v2 and a2 is entering the control volume minus v3 a3 so we can rewrite this as v3 equal v1 a1 plus v2 a2 all divide by 3, knowing that the area is the cross-sectional area, and the cross-sectional area of a p over pi over 4 d square. What we find is the 3 equal 1.07 meter per second. That's all for me. Thank you.